Right. So we talked about immersions and embeddings last time. So just to recall again very quickly. So immersions, it's always when your target manifold is at least the dimension um, um, of the domain manifold, and the rank, this rank condition that I wrote down is, well, so this df is injective, right? So the rank is equal to k, right? So dxf is injective as a linear map, right? So that's an immersion. So locally it always looks like a canonical immersion. And embedding is something which is an immersion, but which is proper and injective. Okay, so that's an immersion. Sorry, that's an embedding, and we saw that an embedding of a manifold, say k-dimensional to l-dimensional here, sort of k is less than or equal to l, is actually always a diffeomorphism to a submanifold of n. Okay, so this M would now be sitting inside capital N as a submanifold. All right, so that was what we saw last time. So, so today the first thing that I wanted to talk about is this theorem, which is that any smooth manifold, let's call it k-dimensional, it's k-dimensional, that has an injective immersion into Rn for some n. Okay, we want to get to an embedding. So we want to get to an embedding, but the first step is that there is some injective immersion into some Euclidean space. By the way, so I'm assuming compact here, I should have mentioned that somewhere here. So maybe I'll sort of remark that so the properness assumption, the fact that embedding has to be proper, is automatic if M is compact. Right? Because what is proper? Recall that proper means the pre-images of compact sets are compact, right? So it follows just from basic points at topology that the pre-images of compact sets in our case would be closed, right? But if you have a closed subset of a compact space, if your M your domain is itself, the whole space is compact, then any closed subset of it would be compact as well. So properness would be automatic, right? So it's helpful to assume compactness of the domain manifold um, at the beginning, and then we'll relax it later on. Okay, so how do you prove this? So how do you prove that if you have a compact manifold, there is an injective immersion into Rn, and in fact, so let me just say that since properness is automatic, so hence it is embeds in. So it's embeds.
Sir, one small question. I mean, what smallest n can we get to?
Yeah, we'll get to that. Yeah, that's one of the goals. Yeah. So we'll show that we can get to 2k plus 1, although there is a stronger theorem that you can get to 2k. Okay, so right now it's just some Rn for some n. Okay, so how do you show that? Well, so what you do is you kind of so here's so maybe here's a sort of sketch to. So here's M, and so there's a compact space. So you can cover it with charts, and you only need finitely many charts to cover it because it's compact, right? And now each chart is an embedding. You can think of it as, well, it's a homeomorphism to some rk, but you can think of that homeomorphism to RK. You can put RK in some bigger space if you want, and so you can think of that chart as giving as embedding into some bigger space. And so the sort of the goal is to put these together, these various charts. So all of these are some charts to RK, but you kind of somehow put all of these images together in some bigger Euclidean space so that it is still an injective immersion. Right? So that's the kind of the broad idea. So how do you do it? How do you put together all these charts? So let's talk about the charts. So let's give them a name. So you call them UI and phi i's. Sorry, there are finitely many of them that cover. Let's call it. Well, I already used. Let's call it little m. Okay, so these are finitely many charts that cover M, and to sort of ultimately patch these together, we will need partition of unity. So let me call it rho i's. So rho I 1 less than equal to I less than equal to M be a partition of unity subordinate to this finite cover. And so the injective immersion that we'll do is the following. So you take phi from M. So we can build it using these charts and these partition of unity. And it's going to give this embedding to this big space where, let me just sort of explain what these things are. So any point P in the manifold would go to rho 1 of P times P1 of P. Somebody has a question? Rho M. Sorry?
I think your screen is frozen. Is the screen just I just see the system and embedding it from M3 and KKN so many for
Sorry, I hear you, Ravi. I can't hear you properly.
I think that
Maybe you can sort of type your comment. Perhaps the voice is not coming properly. Okay. So let's one. Sorry. Let me keep this n, and okay. So we'll figure out what the correct dimension is. Maybe I computed it wrongly. Okay. So if that's what your question was. Okay, so and then, so I haven't yet described all the map. So it's rho 1 to rho m of p. Okay, so how many? So what's the dimension here? So remember, rho of p is a. So what does this entry really mean? So phi1 of p maps to rk, right? So these are the charts, phi1, phi2 to phi p. So rk. And this so that's a vector. This is a vector. This is an RK, and this is a real number, right? So you just sort of multiply every entry of RK with the real number. So this entry really belongs to RK, and each of these M entries belongs to RK, and then these are again some real numbers, and there are M of them, right? So it's basically sort of M times K plus M. Okay, so maybe I wrote it wrong, right? So this is R to the M times K plus 1, if I write it this way. Okay, so this is a map, all right, and I claim that this is the embedding that I was wanting to kind of have to some Rn. So right now this is the sort of the dimension of that big Rn that we can get. Sort of somehow this seems to depend on the number of charts that you're covering by also. But we'll later refine this and do a better version of this embedding. But why is this injective? So maybe let me just say that claim is this phi is an injective immersion, which is in this case, let me remind you, this is means that it's an embedding. So there are two things that we have to say, that phi is injective. So why is that true? Well, if you know phi of P1 equals phi of P2, right? So then what you get? So you know that so if this happens, then in the right hand side, all these two vectors that you get are all are the same. That's what this assumption is, and so then the corresponding entries are all the same, right? And so you can get, if all the entries all the same, so let's look at these entries for now. I mean, these ones were row 1, row 2, etc. So you know that not all of them can be 0, right? Because any point P belongs to the support of some one of these rows. Okay, that's how one used to construct these partition of unities, right? They have to add up to 1, so they can't all be 0. So suppose sort of row 1 of P1 is not equal to 0. But then we know that this row 1 of P2 would also be the same. That's our assumption, right? This entry, sorry, so let me call it row I. Sorry, so I'm kind of confused these indices. So let's say, suppose row I of P1 is not equal to 0. That's the same as row I of P2. Okay, so for some, this is for some I. All right. Okay. So this entries have to be equal if we are assuming that these two vectors are the same. But then you look at the ith one of these guys. Okay. So then what happens is that row I of so then we know from our assumption that row I of P1, phi P1 is equal to P2 phi of P2, right? But then since these are not 0, these factors cancel, right? So phi of P1 equals phi of P2. I forgot to also sort of say that if this happens, right? So if P1 and P2 are both non-zero, this means that P1 and P2 are contained in the same UI, right? Because remember that P1 and P2, they have to be in the support of row I, and remember that this is contained in UI. This is sort of how we construct a partition of unity. And so they're both in the same chart. And so if you also have phi of P1 equals phi of P2, this means that P1 equal to P2, since phi is injective. Right? Phi is a chart, and so it's a homeomorphism to some open set in our case. So in particular, so 2 points in the chart have to go different. Well, 2 distinct points have to go to 2 distinct points, and the only way that the images are the same is if they were equal to begin with. Okay, so that's the proof of the injectivity. Okay, and I have to sort of push things down as usual. So what about immersion? So how do you prove that phi is an immersion? Well, what does the derivative of at a point look like? So immersion means that this derivative is injective, right? So that is, you want dp of this map D capital phi is injective for any p in M, right? So how do you show that? Well, let me add a page. That's one way, sort of pushing down things. Right. So what does that dp of phi applied to some, let's say x is some tangent vector at the point p on M. So what does this look like? Well, this derivative, we know the map phi. It's these maps, right? So at each, it's this sort of vector, right, where every coordinate is this map. So if you talk of the derivative, sort of you can replace. Yeah, so it's you can take the derivative of each of these coordinates. Okay, so this and create the so you can build the matrix that way. Okay, so it might as well talk of so what these each coordinate, what this derivative looks like. So I'm going to sort of do dp. I'm going to think of this as dp of rho I phi I dp. Well, we start with 1. So rho 1 phi 1 dp of rho 2 phi 2, and so on, dp of rho m, rho m, followed by dp of rho 1 to dp of rho 2, right? So you can think of so you can put together the total derivative. Well, this applied to x, right? So I'm already applying it to x. All right. So so what does an individual thing look like? So suppose I do dp of rho I phi I applied to x. Well, the Leibniz rule will tell you that this is the same as taking x of rho I at p. Okay, so remember itself a derivation, right? And times phi I of p. Okay, and the derivative of these rho i's by themselves, this you can, by definition, you just take them to rho I of p. Okay, so now, so suppose all of these are 0, right? That's what you want to check. If it's, you want to check that this dp of phi is injective. So if it happens that you get the 0 image, right? So the image is some 0 vector. So then all of these sort of these constituent terms are all 0. So then you want to say that this x you started off with is 0. That's how you can show that a linear map is injective, right? So suppose all of these are 0. Well, this means that that in particular that sort of yeah. So these guys are all 0. Right, and so yeah, sorry, I forgot to add another term here. By the Leibniz rule, you have 2 terms here, right? So yeah, so I'm going to add this plus x of phi I at p times rho I of p, right? So these are the 2 terms in the Leibniz rule. So this equality is the Leibniz rule. Okay. Right. So if these are all 0, then this term here vanishes for all of them, right? And you're left with these, right? So and moreover, for any p, you can pick some p, some I, so that row I of p is not 0. Okay, so so then let me come back to this. So then pick an I such that row I of p is not 0. So we have so x of row I of p times row I of p is equal to 0, but that just means that this is equal to 0, right? So then so we have this equals 0, which is a contradiction because phi I is a chart, right? So this is a contradiction since phi I is a chart and hence is an immersion. Okay, so it's a it's a diffeomorphism to its image after all, right? So and then this left-hand side here is nothing but the derivative, right? So maybe I should have written that here. So this is by the definition, this is the derivative of the map phi I applied to x. So if this is equal to 0, okay, so I should have said, maybe I shouldn't have said it's a contradiction yet. It just says that x is equal to 0, right? So so let me just do that instead. So this implies, so this whole discussion then implies that x is equal to 0, since phi I is an immersion. Okay. All right. So this is how you prove that it's both injective and an immersion if you define your map this way. But as one of you also asked, this is not quite efficient. So you can ask whether there is some Euclidean space that depends only on the dimension of the domain manifold, right? So that you yeah, so that any m-dimensional manifold is a subset of Rn. Okay, for that n. So you can ask whether you can make this better, right? You can improve this result. Maybe you don't need so much of dimension to begin with. By the way, before that, I also wanted to note that this. Can you
go back to the proof?
Yes.
So here is you have x of phi I of p, and what does this mean? We have seen d phi I of x, d phi at p of x.
Yeah. So maybe I shouldn't have written as x of p. It's sort of I should let me just write. These are all x. So I wanted to mention p because this is where all the action is happening. But yeah, it's just x is already at p, right? It's a tangent vector at p. So yeah, thanks. This is, maybe I should have written this. Okay.
So x of pi, what does it mean? I mean, x of pi is is a map from the manifold to Rn.
Yeah, it's a map not of manifold, it's on a chart. But yeah, so x is a derivation. Remember, x is a derivation, right? So x
it
of
acts on a real valued function, right? Not a vector valued function.
Yeah, that's okay. That's true. but you can, sort of, yeah. So I guess you apply so I didn't talk about all that, but you apply it to every component function. Let's think about that way, right? So maybe I should have mentioned, yeah. So you're absolutely right. So you can think of everything break everything up into components and view it that way. Okay, so yeah. So I mean, there is a, yeah. So I guess, yeah, it's something that you can. Yeah. So it's
Yeah, I guess we can prove this identity also by
yeah.
applying
So
a F
I
on.
didn't want to impose so much of notation, but you can just imagine that all these phi1, phi2, etc., right? Instead of these being vector valued, I break them up even more, right? Each phi1 of p is like phi11, phi12 up to phi1k, right? Because it's k dimensional, right? So and then you apply all these things that I was saying to those guys. So yeah, I didn't want to add too many subscripts. So I just wrote it like this, but yes, you're absolutely right. These are a priori, these are right now vector valued, sort of functions, where we didn't really see how x acts there. But instead of these being vector valued, you can think of the component functions and just apply all that I said to each of those component functions. Okay, so ultimately we are okay because we just want to sort of equate everything to 0, right? And so that makes sense. And so even in the sort of, yeah, so when I say that this phi is a chart, this equals 0, this is really 0 for every component function, right? So I1, I2, I3, and if it is 0 for every component function, then you can see that you can check that it contradicts the fact that phi is an immersion. Yeah, so you're absolutely right. So you have to sort of maybe write this with these additional, I don't know, maybe I didn't write it properly or efficiently, but you can break everything up into component functions and then do the same arguments. But this is sort of what you need to do. Basically, this is sort of giving a kind of an overview. Okay, so does that help? It could be
Yes.
confusing. Could be
Yeah.
confusing, but I hope that you can sort of sort out all the details. Okay, so sort of you can prove it in a way that you like. Okay, so
okay.
yeah.
So I mean, tangent spaces behaves nicely with the product. I mean, TP1, P2 of N1 cross N2 is TP1 N1 times TP2 N2, is it?
Yeah, absolutely. Yeah, that's right. Yeah. So yeah, I guess one can use that too, right? So the induced maps on product spaces is also sort of the induced, so the product of the linear maps, right? Things like that. Okay, so all right, so the proof actually proves something stronger. So it proves that you can embed, so can embed M into some Rn as long as, so it could be non-compact, but as long as you can cover M with finitely many charts. Okay, so this is because that's all we needed for the whole thing, right? So you need to cover M with finitely many charts. That's why we use the compactness of M. But that need not necessarily be, sort of only true if M is compact, right? You could have a non-compact manifold, but you cover it with finitely many charts. Charts are just open sets that are homeomorphic to some open sets of Rn. These open sets, could need not always look like open balls or something. So it might be large in some sense. Okay, so it can cover the whole non-compact manifold, finitely many of them. Okay, so this is going to be, this note, this observation is going to sort of be useful later on when we talk of non-compact manifolds, right? So anyway, so here's the statement that we are after. So here's what we really want to prove. So we want to prove the Whitney embedding theorem, and this is the following thing that, well, it's sort of simple. Any k-dimensional, I used to call it, calling it a k-manifold, right? So k-manifold, let me write dimensional. So any k-dimensional manifold, smooth manifold, of course, embeds in R to the 2k plus 1. So this is an improved version of what we just discussed, because now we got the space and the target space to be supposed to be some dimension, not depending on anything else other than the dimension of the domain manifold, right? So it's just R to the 2k plus 1. And in fact, let me sort of remark that later, so he also proved, I mean, this Whitney proved, so improved this actually, so improved this to R to the 2k. So in fact, any k-dimensional manifold embeds in R to the 2k. Okay. Yes, also assuming the manifold is, there's no assumption on compactness. Okay, so this is sort of any k-dimensional manifold. Okay, so we're going to prove this theorem. Okay, right. So we're going to prove this fact, compact as well as non-compact. And so what's an example, by the way, of all this? So if k is equal to 2, if you're a surface, right? So so not all surfaces can be embedded in R to the 4. Sorry, R to the 3, right? So, but Whitney tells you can embed it in R to the 4, right? And so, what's an example of something that can?
Klein's bottle.
Yeah, that's right. Yeah. So the Klein bottle, as you know, is you obtain it by taking a cylinder and then gluing this to that, right? And so if you want to sort of twist and glue it so that these directions match, you can't quite do it in R3. Okay, so sort of it passes through itself, as you know, right? So it's kind of, you can only do it, you can't embed it. Embed needs to be an immersion, to be injective, but you can, but if you allow it to pass through itself, not be injective, then you can do that, right? Of course, if the arrows are different on the two boundary circles, then you can do it. It's a torus, right? But if the arrows are the same, it gives you a Klein bottle, and that you can't embed it in R3. And the proof of that requires some algebraic topology. So usually one sees it at the very end of the algebraic topology course. Okay, so the proof of why it cannot be embedded in R3. But in any case, it's a fact that this cannot be, so this Klein bottle cannot be embedded in R3, but you can embed in R4, and that's easy to see because you can just, sort of, the point is that you have one more dimension now. If you're in R4, you see this picture, but you have one more direction to push along, and so you can push it both dimension to make sure that this intersection that was happening here doesn't happen anymore. Okay, it's just like, sort of as a sort of a toy example. If you have sort of two lines intersect in R2, but if you're allowed to move in some sort of the third dimension, then you can just hop across, sort of go above and then kind of avoid the intersection, right? So more room helps. Okay, so this is why the Klein bottle can be embedded in R4, and in fact any surface can be embedded in R4, and that's what sort of this improved version of the Whitney embedding theorem says. But in the case of surfaces, it's not, it's not hard to see. I mean, once you know how to do a Klein bottle, you sort of, the classification of surfaces basically gives that, so only bad things that can happen are some things like this, where you do have some kind of intersection happening, but if you have another dimension, you can just push it in that. Okay. All right, but we won't prove this improved version. We'll prove this Whitney embedding theorem. Okay, so any k-dimensional manifold embeds in R 2k plus 1, and there are two ingredients that we need for the proof, and one of them is Sard's theorem. Okay, so so let me come to that now. So what does Sard's theorem say? Well, you'll have to recall the definition of regular value, right? So maybe recall that if your f is from m to n, y in n is a regular value of f if well, basically this derivative is surjective whenever f of x is equal to y. So for every point in the pre-image, this is surjective. Okay. This also says that if your y has no pre-image, right? If this value y is not hit by the image at all, then it's also regular, because this condition is satisfied vacuously. Okay, so the pre-image is an empty set, so you don't have to check anything. It's automatically regular. Okay, this is something to keep in mind. Okay, so what is Sard's theorem? Sard's theorem says the following. So that if you have any such smooth map, maybe I should write things down. This is Sard. So so if f from m to n is a smooth map, so almost every point is a regular value. So there are plenty of regular values. So it's a very useful theorem. All right. And what does almost every mean? So here, and I'm going to describe. I have to describe what almost every means. Okay, so almost every means that the complement of the set of regular values has measure 0. Okay, so you've come across probably this notion of full measure and 0 measure, but I'll sort of recap a little bit of that for what is enough for this discussion. Okay, but let me also remark that there's this things in the complement, things which are not regular, has also got a name. So a point that point of n that is not regular is called a critical value. So sometimes the Sard's theorem is stated that, as if you have a smooth map, then the set of critical values of f has measure 0. That's sort of an equivalent statement. Okay. By the way, a regular value, when I say regular value, it really means a regular value of f, right? So this sort of, that's maybe understood, but let me just add that here in the statement. Right. So okay. So what does measure 0 mean? So let me sort of recap a little bit. So you kind of probably seen this notion in Euclidean spaces. So let me recall what it is in Euclidean spaces. Let's say some subset of RL. We'll be talking of subsets of n, which is maybe some L-dimensional manifold. But for now, let's recall what some subset of RL, when that has measure 0. So that has measure 0 if it can be covered by, so one way to define it is covered with boxes, right? Parallelepipeds, if you want. So countable number of, let me call it boxes, rectangular boxes. So let me call it rectangular boxes. Let's call it S1, S2, etc. Maybe I should have said that for any epsilon, it can be covered by countable number of rectangular boxes, such that if you add up the volumes of all these rectangular boxes, the volume of a box is easy. It's the product of the sides, right? So if you add these up, it's less than epsilon, right? So for any epsilon, you can do this, and that's when you say that rectangular. So here, let me actually say what rectangular box is. So SI is something like a product of maybe, let me make it close just to. It's a product of intervals, right? That's what a box is. Okay, so sort of AI, BI cross, well, sorry, I just use this notation here. 1, 2, sorry, L, right? So that's a box, and the volume of any of these boxes, L, is just the product of the length of the sides, so BI minus AI. Okay, so in fact, here you can make these open also if you want, but it doesn't quite matter. But anyway, so that's what a measure 0 set is. For any epsilon, you cover it with a set of size, a volume at most epsilon, and so you can. So this is measure 0. And a manifold now, so now that you'll be on an L-dimensional manifold, so a subset Y in N. So this is now an L-dimensional manifold. You can try to now do the same kind of definition, except that you have to do it in charts, right? So let me call it not Y, but let me call the subset C. Well, okay, let me call it Y. Right. So is measure 0 if something, right? So the first case is, so if it's contained inside a chart, then it's the usual definition. If Y is contained in U, which is a chart of N, so then sort of Y is really sitting inside RL, and the previous definition applies. Okay, or so if it is not contained in a single chart, then you can break it up into pieces. Sorry, this is y. You can break it up into y1 union y2, sort of countably many pieces where each yi is contained in a chart. Just by this taking intersection. And you know that there are countably many because n is second countable. So our manifolds are by assumption second countable. So you can always cover it with finite with countably many charts, and so you can just take the intersections. So you can do that, and then you can say, and you can require, and sort of each yi is measure 0. So one advantage of sort of something being measure 0 and in this definition is that sort of countable union of measure 0 sets is also measure 0, right? So anyway, so this is that intuition kind of still applies in this case. So you can say that a set is measure 0 if each piece contained in a chart as measure 0, but it's still you need to verify that this definition is well defined, right? That doesn't depend on the choice of a chart, etc., etc. So somehow you kind of still need to sort of, when I define it this way, you need to verify that this definition is independent of which chart is independent of charts, right? It could be, I mean, why can't it be that you take one chart, it is measure 0, another chart it's not, etc. Right? Okay, and that's sort of guaranteed by the following proposition. So you can so here's a slightly more general fact. So suppose, so let U be an open set in Rn, and suppose F from U to Rn, same dimension, be a smooth map. And then if you have some subset, let's call it A, is so this has measure 0. So maybe I'm saying is of measure 0, but I mean, so A has measure 0. So then the image under F also has measure 0. Is also of measure 0. So that's the proposition. Why does this help us here? Well, it's because if you have two charts, they differ by such a map between open set in Rn to Rn, right? So because suppose you have a picture where you have a manifold M, some set A is sitting somewhere, but you have sort of two charts. One is phi mapping somewhere and psi mapping somewhere else. So this phi, suppose here, this is sort of, oops, maybe I'm sort of, I should use different colors. So sort of phi of A somewhere here, maybe A is this red guy. So phi of A sitting there, and this is psi of A. So if phi of A is measure 0, then psi of A is the image of phi of A under this transition map, right? So which is this diffeomorphism, right? So and so you really need to prove for the well-definedness, you really need to prove this for diffeomorphisms. The diffeomorphisms measure 0 sets to measure 0 sets, but we can actually do better. We can just say any smooth map from Rn to Rn, or any open set in Rn to Rn, takes measure zero sets to measure zero sets. Okay. Okay, so I hope it's clear why this proposition implies that it's, I mean, you can check that using this proposition is easy to check that the definition is well defined. But how does this proposition, proof of the proposition work? Well,
Change of variable formula.
Yeah, that's right. But I'm not necessarily, I mean, you're right, but the change of variable formula, yeah, sort of assumes a lot of things.
Integration or Riemann integration.
Yeah, that's right. So all those questions arise, right? So here I've defined them. I've just defined measure zero, right? So I've just defined what measure zero is. I'm not talking of what the measure is precisely. Okay. So yeah, it is the Lebesgue measure and so on, but I haven't gotten there, right? So this is just measure zero. So, but one can prove it just from the what we've defined so far also. Okay, and the proof.
In particular, U is a subset of Rn, so we can talk about Lebesgue measure on U.
Yeah, but suppose you don't know about Lebesgue measure or things like that.
I see. Yeah, only we're using that definition.
Yeah. So how do you know that Lebesgue measure zero sets have this property? Then you'll have to prove that, right? So if your Lebesgue measure is zero, then this is always true. They can cover countably many rectangular boxes, etc., right? So you don't know that. So we are defining measure zero sets this way. Okay, and so this is what we need to use. Well, so let me tell you how this proof goes. It's basically something we also saw. It's using something we saw earlier. So
so do we need like epsilon by 2 to the n kind trick?
Epsilon by 2 to the n. Not quite, not here. Okay, so what you can do is the following. So it's so first of all, so I claim that without loss of generality, you can assume that this set, in fact its closure is compact and it's contained in a chart. Why? Because otherwise, I mean, so let me just say, otherwise you can just decompose it into countable union of things which satisfy this. Otherwise, just consider A is A1 union A2, etc., where each of these AI is compact. Sorry, AI closure is compact and contained in some chart UI, and then if we have proved this, basically the point is I want to say that so it's maybe I should have said instead of without loss of generality, I should have said that sort of enough to assume. So it is enough to prove this case. Then when so it's enough to prove with the well, assuming that A bar is compact, because if you prove it for that, then so this argument would hold for all of these A1, A2, because remember all of these would be measure zero as well. If your A is measure zero, all of these would also be of measure zero. And so your argument will hold for all of these. And so you would have shown that the images of A1, A2, etc. are all measure zero. And then the union of all these countably many measure zero sets will also be measure zero. Anyway, so it's enough to prove with this assumption. So this, let's call this chart U, right? So this assumption kind of makes sure that you can work in sort of Euclidean space. You can think of, you know, sort of everything happening in Euclidean space because you are in a chart, right? And so so you can actually use another property of Euclidean spaces. Let me write that out. So then there exists an open set W which contains this closed compact set, and those closures contained in U. So it's sort of sitting, and this omega closure is compact. So you don't want this chart to be too big. You can sort of imagine that it's so maybe this chart was some U, your A was sitting there, but you can sort of choose a nice enough open set W so that W closure is contained inside U. Okay, so you are in this kind of setting, and so all the action would now be happening sort of in this subset, which is some subset of Euclidean space. Now it's a subset of Euclidean space whose closure is compact. Maybe I should just do the closure here itself. So we are just you were just working in this closed in this compact subset. All right, so your subset A is living in this compact subset of Euclidean space. Okay, and you have a map sort of defined there, right? So this map is taking this, to Rn, right? So, well, we were already in the beginning of, in the beginning we had assumed that we were already in Rn. But the point is that we can you can assume that we are in some compact subset of it. Okay, so and if we are in a compact subset of it, so since this W closure is compact, so there exists some bound on the derivatives. Okay, so in particular there's some constant m such that f of x minus f of y is less than, or maybe I should just say strictly less than m times x minus y. Okay, for all. This is something that we've seen, that if you are a smooth map defining some compact subset of Rn, then you would have a bound on derivatives, and once you have a bound on derivatives, you have this sort of Lipschitz condition. Okay, well, okay, so anyway, so we kind of only proved it perhaps for rectangular. We kind of saw the proof for rectangular boxes, right, or convex regions, because we needed to draw straight lines between points. But ultimately we're going to use it for such things because we're going to apply it to these rectangular boxes that cover A. So remember that A is covered with rectangular boxes whose volume adds up to less than epsilon. So let me just write that. So if S is a rectangular box in W closure, so then f of S is going to be contained in some other rectangular box in Rn, where the volume of this rectangular box is going to be less than some constant depending on this m times the volume of S. Okay, so why is this? Well, it's because points in S are going to be moved only by this factor m, right? So if you have, let me just draw it in 2 dimensions. So if you have somehow this box side lengths A and B, this is inside sort of W closure, then sort of if you map it by F, and at most you'll sort of be mapping to something which is, so this is sort of less than m times A, and this is less than m times B. So the volume will go at most m squared. Okay, so I don't want to sort of keep track of those, how that factor depends on M, but I'll just call it M prime. Okay, so this M prime. So you can't map it to too large a volume box because all your derivatives are bounded, and the derivatives give you this Lipschitz property, and you're basically working inside some compact region of Euclidean space where all these derivative bounds hold, and so on. Okay, so this is what guarantees that that whatever the image is. By the way, the images need not all be a box. Maybe I shouldn't have drawn it with straight lines. I mean, but the image is some wiggly thing, right? All the sides map to some sides, but they're not too far apart. So you can actually sort of, it's easy to then enclose this region inside a box. Okay, then that's going to be my S prime. So maybe this is sort of f of S. So this region inside is f of S. Maybe I should shade these a bit. So this box gets mapped to this region here, but you cannot. I mean, this is some Euclidean geometry, right? So if you have some things where these diameters satisfy some constraints, then you can always put it in a bigger thing, which is not too larger in volume. Maybe it's sort of the size is maybe twice the volume of whatever this shaded region is. But so in particular, so you would have that sort of, since A is measure 0, you have this covering of A with all these boxes on the left, which have small, which add up to less than epsilon. So A has measure 0, which is the assumption, implies that for any epsilon, A, this can be covered with these rectangles, right? Such that the volume, if you add these volumes up, it's less than epsilon. Sorry, it's less than epsilon. Okay, and by the sort of what we just discussed, this implies that f of A would be covered with all these slightly bigger, perhaps this SI primes. So let me call it SI prime. So this S prime is this bigger thing that contains this image, right? So for each of these boxes, SIs, you have these SI primes, and then the volume of these SI prime is going to be less than the M prime times the volume of SI. So so if you add them up, this will be less than M prime times epsilon. Okay, and this just means that FA has measure 0, because this holds for any epsilon. Okay, so by any epsilon, your f of A, you're covering with boxes, these SI primes whose volume is less than Mi times epsilon. Of course, this Mi times epsilon is, you might as well say epsilon here, right? Okay, so so this is the proof of why the image under a smooth map of a measure 0 set has measure 0, if one defines measure 0 like we did. Okay, so this makes sure that this definition is well defined, and it actually also gives us this corollary. So this is what is actually going to be useful for us. This is sometimes called the Mini-Sard theorem. I think Milner's book on topology from a differentiable viewpoint has this, calls this Mini-Sard, and it just says that let U be an open subset of Rn, f U to Rm be a smooth map where m is bigger than n, so then f of u has measure 0 in Rm. Okay. Okay. So what's the proof of this? By the way, this is also a corollary of Sard's theorem, but we haven't proven Sard's theorem. Okay, and I won't prove that because all that we will need is this corollary of it. Okay, this mini Sard theorem. Okay, so I mean, I guess one exercise, maybe exercise this week, is to show how, or maybe this will be your exercise. So Sard's theorem implies this statement, implies this also. Okay, but we are not going to prove it using Sard's theorem, but we are going to prove it as a corollary of this proposition we just proved. Okay, so we want to show this using proposition. Okay, so so how do you, so in other words, if you, whenever you are mapping some to some bigger dimensional subset, some subset contained in the Euclidean space of bigger dimension, then your image will always have measure 0. This is what this is saying, and I guess one example is when so you have this that immersion, one of these canonical immersions we were talking about, right? So if you have a sort of Rn to Rm, right? So this, let's say, so this was the picture, right? So you had R2 mapping inside this Euclidean space, or let's say R3, and it's sitting in as this plane, but then that plane would have measure 0 in R3. Okay, so that's sort of the example to keep in mind. And the point is that well, you can use this this canonical immersion to do your job. Okay, so so if your f, so suppose let me just say enough to prove. So let me say this is a canonical immersion. Let me write that down. We have a canonical immersion of Rn to Rm. So enough to prove that if you have a compact subset of U, then f of k has measure 0. So in other words, you can assume without loss of generality that okay, sorry, I just missed that measure 0 subset completely, but right, okay, sorry, I can write it as f of u, but instead of u an open subset, I would have measure 0 and then the union of measure 0 sets measure 0. So we're going to use that assumption, and the point is now that so if you have some kind of compact set, so it's easier to imagine that your map is defined in some compact set. So if your map is defined in some compact subset, you as mind on the submanifold of Rn. Okay, so 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 think of f as defined on on K, which is contained in a submanifold of Rm, where the submanifold is nothing but this canonical immersion. Your smooth map is defined in Rn. Think of that Rn as this hyperplane or something inside Rm. Okay, and so you can define your map there, and so the K is subset is a zero-dimensional. Sorry. Sorry, say it again.
Your voice is breaking. I mean, I did not hear anything in last 2 minutes.
Okay, so let me repeat. So you can think of this F as defined on some compact set.
Also, can you share the screen again? I mean, I can't see the screen.
Oh, okay. Let me share it. Wait, listen, let me stop sharing first. Can you see it now?
No, actually. Okay, I'll try to rejoin.
I can't either.
I cannot see also.
Okay, let me try. Can you see it now?
No, sir. I mean, I can't say any continue. I mean, I'll watch the recorded lecture.
No, I also can't see.
No, sir.
Okay.
All of us are unable to see.
Okay, it's a common problem then. So let me try to see what's going on. Okay. So it's still not coming, is it? It's strange. Let me try again. So now I think it. Okay. Right. So can you guys see this now?
Yeah.
Yes.
Okay. Yeah. So the point of this sort of the idea of this corollary is as follows. You think of this Rn, which is lower dimensional, as a submanifold, as some kind of hyperplane sitting inside Rm. And now your function is defined on that lower dimensional thing. You might as well talk of a compact subset. It's sort of, you can reduce it to, instead of talking of an open subset U, if you like, you can talk of a compact subset. That's not that important. But now the point is that if you think of something sitting in a hyperplane, so this has measure 0, all right, because you can just sort of, if something is, let me draw a sort of one-dimensional lower. So if something is sitting on this line, if you have a subset somewhere sitting on this line in R2, then you can sort of trap it in boxes of smaller and smaller volume, because you can sort of take this height to be epsilon and just then sort of covering this compact thing, and then let epsilon goes to 0. All right, so this this subset K has measure 0 if you think of it like this, as sitting inside Rm. Okay, and then you want to say that that you use the proposition to say that the image of a measure 0 set has to again be measure 0, and that's what you wanted. Okay, except that you need an intermediate and one more step, that you need to extend F to some. So F A prime right now it's only defined on the submanifold. Okay, if you want to apply the proposition, you want to define it in Rm or some open set of Rm. itself. And the thing is that you can do it. I think this is one of the problems in this week's problem set, which is due Wednesday. So you can extend f to find on a neighborhood of K in Rn. Okay, so the bigger space. Okay, sorry, it's Rm. I should have said Rm here. All right, and now, sorry, this is also R. I got this wrong. So the F maps to Rm. Okay. Anyway, so it's defined on a neighborhood. So now you have you can apply. So okay, so I guess I did anywhere, but sort of K is a measure zero set subset of Rm if you view it as sitting inside this hyperplane, and so is f tilde of K, which is nothing but f of K. Okay, so so this is the sketch of, maybe I went over it very fast because I was completely out of time, but over time, in fact. But the point is that this is how you prove this corollary, that if you are mapping into a bigger dimensional space, then your images also always have measure zero. Okay, and this is going to be crucial for us in the proof of the Whitney embedding theorem. Okay, this is what we are going to use. This is also a corollary of Saad's theorem, which is what I stated at the beginning, but we are not going to prove Saad's theorem. Okay, Saad's theorem, I leave you to, I mean, you can look up, I guess one of the books that has a proof is Milner's book called Topology from a Differentiable Viewpoint. So you can have a look at that. And you can find it in many places. Saad's theorem is it's something that one has to sit down by oneself and sort of read the proof of. It's slightly, sort of heavy on notation, complicated. But once you understand the basic ideas, it sort of should be easy enough to follow. Okay, you just kind of have to follow your nose and prove this. It's sort of a strong statement. But this is the statement of this corollary is all that we really need. Okay, so and this is and we've kind of proved it modulo this extension, which is sort of something that is an exercise, right? So if you have a map defined on a manifold, submanifold, you can always extend it to some open set in the bigger manifold, and this is what you can now apply to get the job done. Okay, so any questions? Let me stop the recording now.